So now our question is, how can we approximate the original high-order model by low-order integer-order models? And the idea I use is the so-called optimal rational approximation or optimal model reduction technique. Because the original model, I assume, is G1 or G2, which are quite high. The order of them are quite high. So it is integer order. So I can use optimal model reduction techniques to find an approximation to the original system. This is G1, G. order. So what we need is to introduce is to find a low order approximation to it, and I've written a piece of code, OPT APP, where we can select the orders of the fitting model, and this is the original model of order 56. And here I can use an option to say whether we need a delay in the reduced order model. If it is 1, then a delay will be of 10. If it is 0, then there's no delay. So with the use of this function, GR equals to OPT APP, and the original model is G, and the order selection I can use is 3 in the numerator and 4 in the denominator, and with no delay. So after optimization process, we can find the future.
How do you know you're getting a good approximation?
You can try different combinations and check the final fitting results.
But
I will send that one later to you. Actually, this is the code I use. You can compare either the body diagram to see whether the fitting is good, or you can compare the norm of the error. You can extract, you can find G minus GR, which is the error. You can find the norm of it and see whether it is small enough. I think the best way is to use the body diagram comparison.
Are you doing a search inside? Are you doing a search?
Yeah. Numerical approximation method. And for the original system, which is the order of it is quite high, it reaches to 56. By approximation, I think for this kind of approximation, the norm of the errors is decreasing to certain values. And since these two are very close, if you further increase the order of the approximation model, you may not get significant reduction
what
in
about
the result.
increasing R? Like you kept R constant. What about you change R?
R?
Like you have these two.
Well, you can try different values, but I think when R is smaller, then it might be easy to control.
And when you had, as ShangYu asked, 9 and 10, you said you work by experimental results.
Oh, that's just for derivative approximation.
But for that specific function?
No, I tried several functions. It works well. The target here is if it is better than the original filter, I can accept it. So I tried quite a lot of functions, actually tried quite a lot of orders, because that's only approximate for the fractional order differentiators, not for other terms.
Yeah.
So I tried many terms and finally came out results for the value of B and D. You can change it if you like, but you have to make sure that the fitting is good for certain functions. Right? So, any other problems? Well, actually, you can try different combination of R's and N's and triangle. And if you think that the error, the norm of the error is not decreasing significantly, I think the lowest order is the best. You should not increase the orders.
I was just asking because how you know that 3, 6
You can
won't give you a way better result than
you can calculate them and you can add the result. Actually, I've done it, but I omitted it.
Oh.
Since there isn't any significant improvement. You can try for them, and I think it is quite similar to the AIC criterion in system identification. I'm not quite sure whether you know this criterion. It means that for certain order combination, the criterion may decrease, but for certain values, it may not. For certain combination of orders, the criterion may not decrease significantly. So we better use the lowest possible order. It is not necessary to increase the order anymore. It is quite similar. The curve of the norm of error is also behave something like this. And there are other methods to approximate the original transfer functions, fractional order transfer functions as well. For instance, we can get a frequency response first, and then use the Matlab function such as INV_QS for continuous approximation, or this one for discrete approximation. And we can also find the integer order approximation to the original frequency responses of fractional orders. So we can use this kind of command to find approximations. However, there might be some cases where this method may not work. For instance, for a transfer function like this, we can try the the integer order frequency response fitting to it, and we may find that the error may be quite large. This is the original model or original frequency response for fractional order systems. Well, sorry, we have to draw the fittings as well. I made a mistake there. This is the original this one is obtained. This one is obtained by the fitted model, the integer order model. So let's try the original model. We may see that there are differences. And even if you change the fitting range, you may find that the fitting may not be very good. Again, we should use a line command. This is the phase fitting. So for frequency response fitting, the result may not be very good. So we must be very careful. If we get the fitting model, the first thing we need to do is to compare whether it is close to the original model. If it is not close, we should not use it. So the solutions are we have to increase the orders and then try again. Based on the filters, I have designed a Simulink block so that we can use a Simulink block like this to approximate fractional differentiators. I will demonstrate this part by example. So let's go back to this example. This is a linear system. We have already obtained the time response of the system by the use of LC function.